Thank you for being part of our study today. On lecture number 14, we're looking at optimization problems. Our objective is to find and evaluate critical points of functions of two or more variables. We're going to be solving optimization problems involving constraints and optimization problems that will be involving boundaries. When we talk about maxima and minima, we're starting off here with a two-dimension maximum and minimum, and as you can see here, you can see the maximum here, dy dx is 0, and the minimum here, dy dx is 0. The first thing we have to do is take the first derivative to get the critical points. When we take the second derivative, it gives us the concavity, which means to let us know if it is concave for a maximum or concave for a minimum. And when we take the second derivative, if the second derivative we look at to see if it's greater than 0 or if it's less than 0. If it's greater than 0, we call it a minimum, and if it's less than 0, we call it a maximum. Okay, so now we're looking at the dy dx as it equals 0 for the first derivative, which gives us our critical point. Our second derivative gives our minimum max or our saddle point. Here's what we're calling a saddle point. We take the second derivative. If it's greater than 0, it gives us a minimum. We take the second derivative. If it's less than 0, it's a maximum. Let's look at this example here of y equals x cubed. If we take the first derivative, we get 3x squared. We take the second derivative, we get 6x. And so we would like to know at what point, okay, we have this point here at 0. So if we are looking at x equals 0 and y equals 0, this point, we take the derivative of it at 0, of the first derivative, put in 0, we'll get 0. Okay, if we take the second derivative, and we plug in x equals 0, and we'll get 0 again. It's not greater than or less than 0, so it's what we call a saddle point, which would be right here in the middle where x 0 and y equals 0. Now, we do have some concerns, and our concerns are looking at the local and the global maximums and minimums. As you can see with this graph here, with this function, you can have many max and minimums. And some will be local, and we want the global. We want to find out what the overall maximum is. Functions may have more than one minimum and maximum, as you can clearly see here. The distinction between local minimums and global maximums is our main concern. With this one here, this would be our global, and this would be our global. this be local, 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 local max, local, 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 local minimum. Finding the global maximum can be tricky. Often needs to test all the critical points, or can use a graphical method. As we can look here, we can graphically see. So if we have this two-dimension, this is our two-dimension example. Use the second derivative partial differentiation. And we have some notation here. We have f at xx sub xx is equal to this, the second partial derivative of x, of the function x. F sub yy is the second partial derivative of f as it relates to y, in respect to y. And our f sub x y is our partial as it relates to respect of first taking the x and then taking it in respect to y. Now in our second derivative test, at point AB, we need to find out what point that we're taking this derivative at. We have some tests that we have to do. We have to verify that the second derivative in respect to x is greater than 0. We want to also verify that the y, taking the second derivative of the function with respect to y, is also greater than 0. And then we want to be able to multiply our second derivative of x and the second derivative of y. And see if it's greater than our f of x with respect to x and the partial with respect to y. And we square it. And then under these conditions, it's a minimum. Now, if we have the f of x second partial less than 0, and also for the y, second partial with respect to y is less than 0, and if we can multiply the f of x partial, the second partial of it with respect to x and the second partial with respect to y, if it's greater than f of xy squared, then it's a maximum. If f of x, the second partial as it relates to x, respect to x, and the second partial of x as it relates to y, if we multiply them together and if they're less than the f partial with respect to x and the partial with respect to y squared, at that particular point, it's a saddle point. If the second partial derivative with respect to x times the second partial derivative with respect to y is equal to the second partial derivative with respect to x and then with respect to y, then it's inconclusive. Okay, so let's look at an example. I think now that you have some knowledge of how to do a maxima and a minimum. Okay, we talked about it in the 2D. Now we would like to look at it in the 3D. Okay, as you can see, this has a maximum and it has a minimum. Okay, and it has boundaries. It's only within confined this space. Okay, at this time, now that you have a little background, we would like for you to look at the three-dimensional of f of x for z equals 4 minus 2x squared minus y squared. We're going to come back. We'll come back and let you try to solve it, and then we're going to come back and solve it with you. So thank you for your first part of listening and being part of our